Um, Today's lab has to do with starlight. Unfortunately, we cannot do the experiment on spectroscopy because that's a lab that you will have to do on campus. That lab, you will be able to measure or to observe these lines that you have been discussing in the lecture and that I kind of show you for the black body radiation lab. So that's the reason why we are not going to be, we're kind of jumping ahead with the labs. The good thing is that you're going to have at least 2 sessions to complete this lab. Now, there is a thing about this lab, you are going to need either to print it or to scan it because the lab is not complete in online, okay? It's missing question 16, 17, all these questions from 16 to 21. So you do need to have, in fact, I don't think it's even, does even have this question, 15. So 15 to 21, okay? So you want to have this with you. Don't rely just with the online demonstration, with the online submission or the online assessment that you find in assignments, okay? That's the first thing. Now, you're going to be using a stellarium to observe several stars. So the idea with this lab is to measure stars, the starlight, the color index of stars. So no, you don't really need to print it because you can answer these questions online, or maybe you can just copy it on Word. You can just see, can I highlight this question and then to a notepad there. So that will be easy, like, no? And you can answer the question like that. But you need to answer all the questions, okay? Now, when you get to this point in the lecture, you will be discussing about how do we measure stars based on their luminosity and surface temperature. So after this lab, we're gonna do a small lab on stellar proper motion. That's a very simple lab. And then we will have a long full lab on H&R diagram, which is a very important diagram that we use to characterize stars based on their 2 main parameters, their luminosity and their surface temperature. Now, the surface temperature, you know already, we can calculate the peak on their spectra. That's what we did in the black body radiation. For this lab, you will just be looking at the magnitudes. So in this lab, we are going to be using the magnitude of stars, which actually relate with the luminosity more than with the temperature. Now, the magnitude can be written in 2 forms, the apparent and the absolute magnitude. The absolute magnitude is basically related to the luminosity. For example, when you look at the sky, you will see some objects that are brighter than other objects. Let's talk about stars. Vega might be brighter than Regulus. Now, there are 2 reasons for that. One reason might be because Vega is hotter, so more luminosity, right? The basic equation for luminosity is this. More temperature, more bright, the brighter it is. It can also be bigger, but it can also be closer to us. So in that equation that you see there, luminosity depends only on the size and the surface temperature. So the absolute magnitude is the one that relates those. Now, it's a logarithmic number though. because luminosities are huge. So we use units, so you use solar units. We take the luminosity of the sun as 1, so we take the log of whatever number is, or a factor of the log. All right? For example, the log of 100 is 2, right? And then we find the luminosities of different stars. For example, Sirius A is approximately 80 times the luminosity of the sun. So if we look at the stellarium, we should find that luminosity related to the absolute magnitude. So when we have done stellarium, I told you magnitude is related to the luminosity. But there is a fact though. I told you to look at magnitude, not absolute magnitude, right? Now we're going to be talking about both. The magnitude, which is the apparent magnitude. So that's the thing though. For the apparent magnitude, we, for example, look at this, right? Sirius looks brighter than this star. So let's take a look. Sirius has an absolute magnitude of 1.44. And this star of minus. So you know what? This star is actually brighter. The thing is that Sirius is closer. Or it might be another reason. Let's see. So 8.6 light years. Ah, there you are. This star is 400 light years away. Sirius A is only like 50 times closer to us. That's already a huge factor for why Sirius looks brighter. So that's why you have to look at the magnitude now. The magnitude is the apparent magnitude, is how objects look from our perspective. So the lower the magnitude, the brighter it is. Sirius has a negative 1.45. This object has a positive 1.5. So from our perspective, Sirius will be brighter. But if we place this object and this object at, I believe it's 100 parsecs, if we place them at that distance, the same distance from us, then we will see that, what's this? Adara is brighter than Sirius if they were at the same distance. That's why we use absolute magnitude. Okay? So there are questions in the lab where they're going to ask you about that. I believe that's in here. Brightest, faintest. When they ask you which is intrinsically brighter, intrinsically brighter, you look at the absolute magnitude, which is actually brighter, basically. All right. Now, as I told you, we use a logarithmic scale for luminosity, but we can also use a power scale for magnitudes. So the difference in magnitudes is scaled by multiples of 2.512. So a magnitude 1 is, no, sorry, a magnitude 0 is 2.512 times brighter than a magnitude 1. The difference of magnitudes is 1, so that's the one. And then you start multiplying by the same number. For example, a magnitude star 1 is just this times more brighter than the second magnitude. But then you multiply 2.512 times 2.512 to find how much more bright is compared to the third magnitude star, and so on. Okay? That's how you will answer this question, by the way. And this.
Can you repeat that? I'm sorry.
So the magnitude scales is based on this number. Okay? And the thing is that this number comes from what we call a stellar spectroscopy. It's a method that we use to measure distances in the sky, and it has a logarithmic equation. I believe it's 2.5 log of m equals to n minus m equals 2.5 log of the distance. Yeah. So it's a logarithmic equation. But what you need to know about this is just that the difference between magnitudes, so let's say the difference is 1, so it's just 2.512 brighter. If the difference, for example, is 2, is 2.512 times 2.512. So it's not double. You multiply, you do the square, right? It's a power relationship. So if you have, for example, a planet, like they give you here later, Venus has an apparent magnitude of -4. Since it's a planet and it's close to us, it will look very bright. So that's why it has a very small apparent magnitude. But then if we compare it to a star like Vega, and I believe Vega has an apparent magnitude of 0, if I'm not wrong. Yeah, you see the apparent magnitude of Vega is 0. So between Venus and Vega, the difference is 4. So you will multiply 2.512 times 2.512 times 2.512 times 2. So 2.512 to the power of 4. That will be the real difference in brightness. Okay. That's how you answer these questions and these questions there. Remember, to answer question 5 and question 6, you need to remember that lower the magnitude, that magnitude, you don't look at, when they ask you for apparent magnitude or magnitudes, you just look at the magnitude. And the thing is that magnitude is something that we use the most, more than absolute magnitude. Okay? Because absolute magnitude is like an intrinsic value that we know based on their size and based on the distance that they are from us. For example, let's take a look at this. Vega has absolute magnitude of 0.57. Let's take a look at the absolute value of Venus. So again, right? If we put them at the same distance, Venus will always look brighter because it's very close to us. Okay, and yeah, it also has a higher. Now let's take a look at two stars. So Vega has 0.57. All right. And what's the distance? 25. So it's very close to us. 5 light years. Let's take a look at Polaris. Okay. So Polaris has a higher absolute magnitude. That means that Polaris will be actually brighter than Vega. So interesting, right? Now, why Polaris looks less brighter? Because like the apparent magnitude of Polaris is greater than the apparent magnitude of Vega. That means that Vega is brighter. It looks brighter from our perspective. That's because the distance from Vega was 25 light years, right? 26 roughly. For Polaris, the distance is 432. So the distance from how they are from us is a factor. And we will take that into consideration when they ask you here, which of the, so you will look at the stars of the whole of the Little Dipper, and you will answer these questions. And then you will explain which stars are closer than 10 parsecs. To know that, you need to look at the difference between the apparent and absolute magnitude. Okay? So you have to compute that. And then pretty much if they are negative, they will be less than 10 parsecs. If it's positive, it's greater than that. All right. Remember, guys, please, arithmetics, all right? You're probably gonna be dealing with integers, negative with a negative, positive with a. So, for example, here, let's do this exercise. If you have to subtract the magnitude minus the absolute magnitude here, what's the value? How will you subtract those two? that minus and minus is positive. 5.61. Let's take a look. That should give you more than 10%. Yes. This is approximately 150%. Right? So there you are. So it's nothing difficult, guys. I believe your goal today should be at least to finish until here. And then the color index. The color index B minus B, you find it here. You need to write that down as well at some point. The color index is about the color that a star looks. For example, Polaris has 0.63. That's a blue filter and a UV filter. But then let's take a look at the bluish star, like Ryan. Ryan is a blue giant. The B minus B is very small. That's because it's a blue star. So a blue star has a lower B minus B index. And a reddish star, let's take a look at Antares, has a high B minus B index because it's a reddish star. All right, guys, so take this lab as kind of going ahead on your lecture. There's no pressure of finishing today. If you don't finish it on Monday, I will probably give you until next Wednesday. All right. Then you will use this equation to find temperatures of the stars. If you get to this point, let me know so I can help you with this. It's basically in a calculator, you have to be very careful. All right. The good thing is that you can always compare. Yeah, you can always take a look at the stellarium and double check, or Google, right? Just to double check your temperature of stars that you get here. All right. So again, if you go to assignments, the lab is not complete. It doesn't have the last 6 questions. So let's take a look at preview. It only has question 1, 2. Let's take a look. Yeah, it only has till here. So you're gonna need to use the manual. Okay.
We're gonna have to use what?
The manual, the lab instructions.
Oh, okay.
Okay. To finish the lab, to answer the last 6 questions.
Wait, and so how are we gonna put the last 6 questions
You
on?
have to send them to me by email, or I guess you can attach them.
Okay.
Okay.
And this lab is due the 26th, right?
I have put it in there, but it's gonna be up to how much you guys do between today and Monday. It's due
Oh, okay.
26, right?
Mm-hmm.
So yeah, I'm giving you more than a week, but if you need more than a week, we'll see.
Okay.
Start working on now and see how far you can get.
Professor, somebody said in the chat that do you want us to have it printed on Monday?
No, because no, not really, because you're gonna be home, right? So
Yeah.
no, you don't have to. You can just copy paste on a Word document or something.
And then just send it to you through email.
Yeah. You can do the whole lab in a Word document as well. It's up to you.
Okay.
Any question, guys?
Not right now.
Start working on it, guys. See how much you get. The first question should not be very complicated, right? It's just stellarium.
For the first question, does it matter like where and what time?
No,
Or
none of the
just-
questions, that doesn't matter.
Okay, just gotta find the constellation and
Yeah,
then
just find the constellation, find the stars.
Professor.
Yeah.
Yeah, for about last week, I did the assignment, but I could not send one of them. The one about the video. I did it, but it was closed before I submitted.
Send it to my email.
Okay, I will. And about the lab, I could not find lambda torus. I put the sign, but I could not find the picture type for them.
Lambda is this. I'll give it to you. The spectral type is B4. B4, okay?
Professor,
Yeah.
for the first question. It says it's looking for constellation Pisces Aquarius. Is it looking for Pisces or Aquarius?
There, Pisces Austronus. That's why it's looking.
Oh, okay.
Yeah, Professor, I have three of them that I could not find.
Which is the other one?
It was, give me 1 second. It was lambda, gamma, and theta. Taurus.
Huh?
It was lambda, gamma, and theta. The lambda, Taurus, gamma, Taurus, and theta.
That's the one. There it is.
Give me one
That's fine
second.
for the today's lab. That's the constellation. Okay. Yeah, that's fine, Maria. You have to go. You have to go. Make sure that you are working on this lab. This lab is not hard, but it's not easy either. You need to do it, okay, carefully. Okay, which is the one that you're looking for?
Lambda, Taurus. I put the
B4.
sign. Yeah, I did, but I could not find the spectral type.
That's B4.
I
For
could not
Lambda
see.
Taurus is B4.
It's here. It's what? I'm sorry.
B4.
B4.
Yeah.
Okay.